In this video, we're going to work an example problem that involves both a sequence and a series in a real-life situation. And not just the sequence in the series, but also we're going to have to evaluate the infinite sum of the series and the limit of the sequence as part of the problem. Now, some of you might find word problems like this unrealistic or overly simplistic, but just note that, for example, this problem is based on, a drug and biology. Well, the people taking a calculus course like this, not all of them are majoring in something in biology. So you can't make these problems too complicated. So just note that these word problems are trying to illustrate the math concept, the possibility of this math concept being in a real-life situation. Okay, so it says a patient is injected with a drug every 12 hours. Immediately before each injection, the concentration of the drug has been reduced by 90%, and the new dose increases the concentration by 1.5 milligrams per liter. What is the concentration after 3 doses? Okay, so we're going to answer part A, but let's keep in mind in the process, we're going to be wanting to find a formula for the concentration as a function of the nth dose. Okay, so we can think about this sequence C sub n. So the first dose, which I'm going to say corresponds to n is equal to 1, but you could start at n is equal to 0, however you would rather start it. But so right after you take the first pill, after that's the first dose is what I'm calling it, the nth dose, the first dose, what's the concentration of the drug in the body? It's 1.5. Right? A new dose increases the concentration by 1.5 milligrams per liter. Okay, now when you take the next dose, what's the concentration going to be? Well, it's going to be reduced by 90%, so 0.1 times the initial dose. Okay, but then plus you just took another dose. Okay, now what's the concentration after the third dose? It's going to be 0.1 times all of this. So we can write it this way. 0.1 times, this would be C sub 1 plus C sub 1. Then 0.1 times, this would be C sub 2 plus C sub 1. Then 0.1 times C sub 3 plus C sub 1. Okay? So you see what we're doing here? It's this, the 0.1 times the value that's being multiplied by 0.1 is the amount of the total amount of drug that was previously in the body when the previous dose was started, right? So we had this amount in the body right after we took the second dose. And then 12 hours later, 90% of that went away. 90% of this went away, right? But then we added another dose. Here, 12 hours later, 90% of this went away. This is C3, but then we added another dose, which was just C1, okay? So with this, looking at this, we can see that we can write a recursive formula for sure, but they're not asking for a recursive formula. They're asking for the actual function of n, but still, let's go ahead and write a recursive formula. Okay, so with a recursive formula, if we look at, for example, the Fibonacci sequence here, we can make our formula not necessarily start at 1 in the sense that we want to, maybe the formula doesn't work for the initial first or second term. So you want to specify the formula is only valid for, n is greater than or equal to like 3, for example. And this just comes into play because of the way you're defining, with a recursive formula, you're defining the nth term as a function of previous terms. So it might be kind of hard to have the first 1 or 2 terms incorporated into the recursive formula. Okay, so like if we ignore the first term, we can see that in general, what we're doing is the nth term is 0.1 times the term before the nth term plus 1.5. That's what we're doing. Now, you could go ahead from here. This is you have a term defined in terms of previous terms, but I would rather do it this way. So I think this works out a little bit cleaner since in general I want to consider this to be the first term when we do the C sub n formula. So 0.1 times C sub n. Okay, you see how these two are exactly the same. This is just a matter of setting it up to where the indexes work out in the way I want. And I believe this is, whenever we get to the C sub n formula, this is going to work out better since I'm starting with n is equal to 1. Okay, so C sub n plus 1 is equal to 0.1 C sub n plus, okay, and then we're going to define the C sub, so n's going to go from greater than or equal to, and we want to define the first term. Now this is the general C sub n formula here, the C sub n. When we derive that, I want to make that start at 1, but this is going to start at, so it's going to be, well, this could also start at 1, and that would mean that, yeah, C sub 1 is going to be 1.5. Yeah, okay. And you need to say this because you can't get C sub 1 from this. Like, you might say, well, why don't we define this for n is greater than or equal to 0? In that case, you put in 0, you'd have C sub 1. Well, what's C sub 0? So is that 1.5? Well, we said C sub 1 is 1.5. And then even if this was 1.5, 1.5 times 0.1 plus 1.5, that's not the first term. So that's why with recursive formulas, sometimes you're going to have to specify what some initial term or terms are, right? F of 2 here, if you put it in 2, that's f of 1 plus f of 0. Well, do they have an f of 0? There's not even f of 0 defined here, you see? Okay, so let's go ahead and use this to answer part A. So after the first dose, C is the concentration is 1.5, C1. Okay, now you might be wondering, well, wait a minute, couldn't we have plugged in 1 into the formula? Yeah, but 1 gives you C2. When you plug in n is equal to 1, that gives you C2. Okay, and that's going to be 0.1 times C1 plus 1.5. Okay, we plug in n is equal to 2, we get C3. That's 0.1 times C2 1.665. So 1.67. Okay, and so that's all it wanted in part A, just the concentration after the first 3 doses. So it wanted C sub 3. Okay, so now how can we answer part B? How can we come up with a general C sub n? In other words, it's not recursive, just a function of just n. And you plug in 1, you get 1.5. You plug in 2, you get 1.65. You plug in 3, you get 1.67, etc. And it works for all n. How do we do that? Okay, well, similar to what we did here with the recursive formula, we just want to find a pattern, but we're not going to have it. For this problem, the most obvious pattern was based on the previous term. The nth term being a function of the previous term. That was the clearest. Okay, but we want to try and look deeper and find a pattern to where each term is not a function of a previous term or the previous term. Or it doesn't have to be, for a recursive formula, it doesn't necessarily have to be the previous term, any previous term, but let's do this process again and see if we can find another pattern that doesn't involve previous terms. So C sub 1 is 1.5. Okay, C sub 2 is 0.1 times 1.5 plus 1.5. Okay, C sub 3 is, and so what we can do here is we know that, so it would be 0.1 times C sub 2, right? That's what how the recursive formula is set up, but let's just input C sub 2. So 0.1 times C sub 2. Then plus 1.5. Okay, let's go one more. So C sub 4 is 0.1 times C sub 3, all of this. So let's make sure we get all of this. 0.1, and then, okay, so yeah, this is kind of confusing here, but we've got 0.1 times the entire previous term. This is the entire previous term, right? And then plus 1.5. Okay, so now with these written out, can we find a pattern here? Well, one thing you can notice is that for all four of these, every single term has a 1.5. So we can factor out a 1.5. I mean, this would be, okay, 1.5 times 1. This would be 1.5 times, let's write it, let's do this, 1 plus 0.1. Okay, here we've got, so here's the 1 plus, we have 0.1 times 1.5 times 0.1 squared times 1.5. So, okay. Now here, we've got the 1 plus, and then it's going to be 0.1 plus 0.1 squared plus 0.1 cubed. Okay, and so we can see what the pattern is. C sub n is going to be 1.5 times 1 plus 0.1 to the first power plus 0.1 to the second power plus 0.1 to the third power. And then we would go all the way to 0.1 to the, it would be n, we ended here with the cubed, and this was C4, to the n minus 1 power. Okay, but what is this? What is this in the brackets here? This is a summation. Right? Because you might be wondering, well, okay, but when we put C sub 1, what happens? C sub 1. I mean, how do these terms aren't even a function of n? How do they get eliminated? They get eliminated because we can write this as a summation from I is equal to 1 to n of, and it would just be 0.1 to the I minus 1. So when I is equal to 1, you get 1. When I is equal to 2, you get 0.1 to the 1. When I is equal to n, you finish with n minus 1. Okay, so let's go ahead and replace this with the summation symbol. Okay, so again, this is still a C sub n, right? We can plug in n. We say if we want the 20th term of the concentration sequence, the C sub n, we plug in 20. We do 1.5 times this sum from I is equal to 1 to 20. So this is a C sub n, and it's the correct C sub n if we're trying to get the amount of drug in the body after the nth dose. And this is correct all the way from n is equal to 1 to infinity. All right, but obviously we want to get a formula, a more explicit formula with n. And we can do that by recognizing that this is a geometric series. Now, it's not an infinite series. It's just going, it's a going just to n. So like a partial sum of an infinite series, you could say. But it's not an infinite series. This is going to n. But we've derived the partial sum formula, the S sub n formula for a geometric series. We did this in the textbook, the calculus textbook, but we also did this in the algebra playlist. That video was included in the calculus playlist. Here's the S sub n formula for a geometric series. Now, this is not the infinite sum formula. This isn't this. This isn't the infinite sum. This is the partial sum formula. Some of the first n terms of a geometric sequence. All right, so we can replace this with this formula. We just need, okay, so what is A? A is 1. The first term is 1. What is R? It's 0.1. So the S sub n is 1 minus 0.1 to the n over 1 minus 0.1. So we've got all right, so this is, so 1.5 is 3/2 times, this is 9 over 10, so we can say 10 over 9 times okay, so and there we go. There's the C sub n. Pretty cool. The nth dose, plug in any value of n. This is for n is greater than or equal to 1. So let's see. If we plug in 1, we've got 1 minus 1 over 10. That's 9/10 times you get 3/2. There you go. Right? After the first dose, it's 1.5. So you plug in any value greater than or equal to 1, and you get the concentration after the nth dose. All right, now part C, what is the limiting value of the concentration? So as the number of doses goes to infinity, what's the limiting value? Now, notice this is not asking us for a infinite series sum. This is just, we're looking at the limit of the sequence. C sub n is a sequence. So it's asking us what is the limiting value of the sequence. Okay, so what is the limit of C sub n? So we do, how do we find the limit of a sequence? We went through an entire section on this. How do we find the limit of this sequence? Well, the main method is, can we just replace n with x and there's no issue? Okay, well, we got 0.1 to the n power. So an exponential, a general exponential, a base to a power. If we, if that started off as an integer, you could do an integer or just or any number. Doesn't matter. Okay, and then if we just subtract that from 1, multiply by 5/3, there's no issue. So we can do, let's take out the 5/3. Okay, with 0.1 to the x, as x goes to infinity, this goes to 0. So this limit goes to 1 with the 5/3 out front. This goes to 5/3. So the limit of this sequence is 5/3. That's the limiting value of the concentration. If you kept taking every 12 hours dose after dose after dose after dose, there would be a limit. 5/3 is 1.67. So we were already getting close just after the third or fourth dose.